GameSide.com. GameSide.com.
How you doing? Computer memory. Computers are simple. All they do is, number 1, move some ones and zeros from RAM to CPU. Number 2, manipulate/change ones and zeros in the CPU. Number 3, move ones and zeros from the CPU back to RAM. Logic gates perform all 3 of these tasks. Computer memory. Address lines. Lines that contain zeros and ones that select which memory location to read or write. Data lines. Lines that carry zeros and ones to and from memory. First and foremost, know your powers of 2. To understand memory, understand the address bus and its relationship to powers of 2. Address lines are labeled A0, A1, ... A to the N. If n equals 3, that would be a 4-bit bus. You'd have A0, A1, A2, and A3. Data lines. Data lines are labeled D0, D1, ... to Dn. What if n was equal to 15? That would be a 16-bit data bus. Is A to the 0 the least significant bit or the most significant bit? I've seen it both ways. If D to the 0 is the most significant bit, it's the sign bit for numeric data. We typically have D0 be the most significant bit, so it can be the signed bit. If 2 bits are used on the address bus, up to 4 registers can be accessed. 2 to the second is 4. As far as the registers go, they store ones and zeros. This is the fastest memory that the CPU can access. Possible addresses with 2 address lines are 00, 01, 10, and 11, selecting one of 4 CPU registers. If the address lines contain 00, you're selecting R0. If the address lines contain 01, you're selecting R1. If the address lines contain 10, you're selecting R2. And finally, if the address lines A0 and A1 contain a 11, you're selecting register 3. The address bus. If 3 bits are used for the address, up to 8 registers can now be accessed. Registers 101 on the address bus select R5 for read or write. 2 to the 3rd power equals 8. If I have 3 address lines, each of which can contain one of 2 values, I can access up to 8 registers, R0 through R7. The possible addresses are 000, 001, ... all the way to 111. Selecting one of 8 CPU registers. 3 zeros on the address lines would select R0. 001 on the address lines would select R1. In this case, 101 on the address line is a 5 in binary, so that selects register 5 to access. Address lines. If 4 bits are used for the address, up to 16 registers could be accessed. As far as the registers go, 1111 on the address bus selects R15 for read or write. 2 to the 4th power is 16. If I have 4 address lines, I can access up to 16 registers. With a read signal, the contents of the register will be placed on the data lines. See the 1101 ... 00 in register 15? Here's the value in register 15. These would be placed on the data lines. 4 ones say select register 15. On a read, the contents of register 15 would be applied to the data lines. Look at this 1101 there. That matches that 1101. I'm reading the data in register 15. It ends in 2 zeros, so the last 2 bits on the data line would be set to 2 zeros. Address lines. If 6 bits are used for the address, up to 64 registers can be accessed. As far as the registers go, all zeros on the address bus selects R0 for read-write. 2 to the 6th power is 64. If I have 6 address lines, A0 through A5, I can have up to 64 registers that I can access, R0 through R63. Let's add a write signal to our register memory. With a write signal, the contents of the data lines will be placed in the register. See the 111 dot 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 111 on D0, D1 through DN? They are placed in register 0. With a write signal to the register, take the data that's on the data lines and place it into memory. If I have all ones on the data lines, then all ones fill address 0. Where did address 0 come from? The address lines, of course. A write signal says write to this address. Take data off the data line and place it into the register. Registers are part of the CPU. The address/data lines are sometimes called the internal bus, and they move ones and zeros between the CPU components. I've drawn this box here to indicate all of this stuff is internal to the CPU. Now, of course, this CPU is not drawn to scale. This is the control unit. This is the circuitry that decides which command to execute. The arithmetic logic unit, or ALU, performs the math and logic operations within the CPU. There are several special purpose registers: the program counter, the instruction register, the accumulator, the stack pointer. These are all special purpose registers. This memory over here is what we call general purpose registers, internal storage to the CPU. There are also special purpose registers like the program counter and instruction register. Registers are the fastest memory a CPU has access to, but there is very little of it. Typically, it is short-term storage while the ALU/CPU is manipulating ones and zeros. Random access memory, or RAM. Computers are simple. All they do is move some ones and zeros from RAM to CPU. From RAM to the CPU registers, to be more specific. Number 2, manipulate/change ones and zeros in the CPU. While that data sits in the CPU registers, the CPU modifies it. Number 3, move ones and zeros from the CPU back to RAM. Take it from the CPU registers and move it into RAM memory. Random access memory, or RAM. Once again, we must know our powers of 2. The address bus. Lines on the motherboard carry ones and zeros connecting the CPU and RAM chips. Data bus. Lines that carry ones and zeros to and from the CPU and RAM. First and foremost, RAM is much slower than registers, but far more abundant. External to the CPU, it requires a bus on the motherboard to transport ones and zeros to and from RAM and CPU. Address bus. Number of lines determine the size of the memory. More bits equals more RAM accessible. Data lines. The smallest addressable unit of RAM is 1 byte, or 8 bits of computer memory. Registers can be 8, 16, 32, or 64 bits depending on the CPU, but RAM accesses data in 8-bit bytes. The data bus may be larger, but a byte is the smallest addressable unit. A0 to A to N, the number of address bus lines determines the amount of RAM you can access. Data bus D0 through D7 means I'm only moving 8 bits at a time. Address bus. The ones and zeros on the address lines make an unsigned integer, which is the address of a specific byte. A small CPU with a 16-bit bus can address 65,536 unique bytes of memory. RAM is simply an array of bytes. Address 000, 0001, all the way to address FFFF in hexadecimal. Random access means you can read or write any one of these 65,536 addresses in any order you desire. 2 to the 16th power is 65,536. That means there are that many addresses accessible through a 16-bit address bus. N in this case must be 15. If N is 15 and there are 16 total address lines, we can access up to 65,000 bytes of RAM memory. FFFF is the largest address you can access in 16-bit. Address bus. 20 bits gets just past 1 million bytes of storage. If A sub 0 is the least significant bit, 0.0101 would be byte address 5 in hexadecimal, And the ones and zeros at that location, 0100, 1011, could be read or written over. Memory is simple. Logic gates take input from the address lines and enable the proper cell. Reading memory, ones and zeros from the cell are placed on the data bus. 2 to the 20th power is 1 million. 20 address bits, A sub 0 through A sub 19, would allow me to access a million bytes of RAM. Now, I don't have room to show you a million bytes of RAM, but if I have 20 address bits, I can go up to a million bytes of RAM. What if I was reading data? If this was the least significant bit, this would be address 5. Address 5 says I want to read this data. If a read signal was sent with this data on the address bus, these ones and zeros would be placed on the data bus. What if my address bus was 30 bits? That gets us just past 1 billion bytes of storage. If A sub 0 is the least significant bit, 0.0011 would be byte address 3 in hex. Not shown are the signal lines into RAM. There'd be a single line into the RAM chip for read, write, enable, etc. With a read signal, the contents of the address bus, 0011, that cell will be placed on the data lines. See the 11001110 at address 0011? Those bits are placed on D0 through D1 D7. If this is the low order bits, this is address 3 on the address bus. With a read signal and address 3 on the address bus, these are the ones and zeros that should be placed on the data bus. Follow the direction of the arrow. This address on the address bus says go to this cell in computer memory. This cell in computer memory with a read signal gets placed on the data bus. With an address bus of 32 bits, that gets us just past 4 billion bytes of storage. Also remember, there's a thing called the control bus. Not shown, the control bus. It's not shown, but they are extra lines that contain timing and command signals. Are they the traffic lights on the motherboard? Yeah, I would say so. The timing signals are the traffic lights that determine when the ones and zeros can go or stop. They control the flows of ones and zeros. With a write signal, the contents of the data lines will be placed in RAM. See the 111.111 on D0, D1 D to the N? They are placed in address 0. 2 to the 32nd is 4 billion. If I have 32 address lines, I can access 4 billion bytes of data in RAM. Now, of course, I don't have room to show you 4 billion bytes of RAM, so I'm just showing you a little piece of the RAM memory. But what we have here is all zeros on this address line. If you have all zeros on that address line, you are selecting byte address 0 for, in this case, a write. The write signal is set, so see all of these ones that are on the data bus? Place all those ones in address 0 of RAM memory. CPU, RAM, the graphics processor, and I/O ports are some of the major components on the motherboard connected by the bus or buses. Once again, this is not to scale, but this box now encapsulates the major components that would be on a computer motherboard. Of course, the CPU, the hearts and brains of the computer, is one of the major components on the motherboard. Other components might be a graphics processor, I/O ports, and of course RAM memory is a major component on this computer's motherboard. Connecting all these components, the CPU and RAM and the graphics processor and RAM and the I/O ports and RAM, is a shared bus of some sort. Some motherboards have dedicated buses, but many computers have what we call a shared bus. It's lanes on the freeway that move cars. They're lanes on the motherboard that move ones and zeros between the various components on the motherboard. Critical to understanding how a computer works. Everything on the motherboard operates at different speeds. The CPU is always the fastest component of the computer. RAM memory runs much slower than the CPU does. I/O is even slower. Control signals for timing data movement are critical. The CPU is running much faster than the RAM, so it has to have timing signals to say when data is ready. Flip-flops, 1-bit memory. Computers are simple. All they do is move ones and zeros from RAM to CPU, manipulate or change ones and zeros in the CPU, and number 3, move ones and zeros from the CPU back to RAM. A flip-flop stores the ones and zeros. The job of a flip-flop is to store ones and zeros. There's several different flip-flops out there. There's an RS flip-flop, a JK flip-flop, and a D flip-flop. Those are 3 examples of flip-flops. And remember, a flip-flop stores a 1 or a 0. It's 1 bit of computer memory. Flip-flops, 1-bit memory. Let's review combinational circuits. A set of gates where the output is 100% determined by the current input. To the left is a 2x4 decoder circuit designed to enable or activate a register. A decoder is a combinational circuit because the input A1 and A0 determine which output D0 through D3 that goes to 1, and it enables register 0 through register 3. Combinational circuits have no memory. They only output what the input at the time determines. This input at the time determines which one of these lines goes to 1. A combinational circuit is a set of gates where the output is 100% determined by the current input. Focus on the input of 0, 0 for A1 and A0. The output is determined by the input. Let's trace some input on these address lines. A0 and A1 have the input of 0, 0. With a 0 on this line, the NOT converts it to a 1 here. With a 0 on this line, the NOT converts it to 1 here. With 0, 0 on the input lines, a 1, 1 is fed into this AND gate. With a 1, 1 fed into this AND gate, it will output a 1 and activate register 0. Only D0 AND gate gets an input of 1, 1. Only R0 is enabled. All other AND gates get at least 1 0 input, so they output a 0. Given n inputs, a decoder will output a single line from 2 to the n outputs. There are 2 input lines, so there are 4 output lines, and only one of these lines will go to 1. Combinational circuit is a set of gates where the output is 100% determined by the current input. Focus on the input of 1, 0 for A1 and A0. The output is determined by the input. The output activates register 2. With a 0 and a 1 on the input lines, that will send a 1 down this line and a 1 down all of these lines, especially that one right there. With a 1 on this line, this tie-in, will send a 1 to that AND gate. So only this AND gate gets 2 1s as an input, which means it activates D2's line, which activates register 2. Only the D2 AND gate gets an input of 2 1s, so only R2 is enabled. All other AND gates get at least 1 0 input, so they output a 0. This is how address lines work. Input of binary 2, or 1 0, enables R2. Binary 3, 1 1, would enable register 3, and so on. I'm not going to show it, but what if I had 2 1s on both of these lines? A 1 on this line would feed into here. A 1 on this line would feed into here, and this AND gate would go to 1, and it would enable D3, which is register 3. 3 on the input address would enable register 3. Flip-flops, 1-bit memory. Combinational circuit allows you to activate a memory cell. How do we store the data in a memory cell? That takes a sequential circuit, a set of gates where the output is determined by the current input and past inputs. In other words, it remembers previous inputs. An example would be a flip-flop. A flip-flop is a sequential circuit that remembers previous inputs. Above is an SR flip-flop, a sequential circuit that remembers if it is storing a 1 or a 0. S is for set. It can be set to 1. R is for reset. It can be reset to 0. 8 of them together can create 1 byte of computer memory. 32 flip-flops can create a 32-bit register. A sequential circuit feeds back into itself. Q is the output of this circuit. This flip-flop is currently holding a 0. See the 0 on the Q line? This flip-flop is holding memory value 0. Not Q is always the opposite. So if Q is 0, not Q must be a 1. This sequential circuit is built out of NOR gates. NOR, of course, means not or the opposite of an OR gate. With an SR input of 0, 0, the circuit should stay the same and Q maintains the output of 0. As long as the circuit has power and the input is 0, 0, the SR flip-flop holds this 0. Before I explain this, remember an OR gate outputs a 0 with an input of 0, 0, so a NOR gate would output a 1. With a 0 on this input and a 0 on this input, two zeros into an OR gate would output a 1 on not Q. Follow the arrow and that 1 would feed into this OR gate. A 1 on this OR gate would mean the OR is a 1, but the not OR would be a 0. With a 0 being stored in this flip-flop and a 0, 0 on the input, it will maintain this value of 0 as its memory. A sequential circuit feeds back into itself. Q is the output of the circuit. Let's change this memory, Q, to hold a 1. Make the S or set input a 1. Make R a 0. I'm looking at this line of the truth table. A 1, 0 for S and R should set Q equal to 1. NOR is the not OR gate, opposite of an OR gate. With S equal 1, its NOR gate must go to 0. If I feed a 1 into this circuit, if I feed a 1 for S into this circuit, 1 and 1 on this OR gate produces a 1, which not OR would turn to a 0. Follow the 0. With two zeros on this OR gate, the OR outputs a 0, but the not OR outputs a 1. What just happened there? My memory cell Q was just set to the value of 1. We're not quite done yet though. Follow that 1 back into this OR gate and it'll put a 1 into that OR gate. A 1 here on this input will ensure that that 0 output stays there. Follow the S arrow to see the sequence. One more time. If this is a 1, I guarantee you the OR would produce a 1 and the not OR would produce a 0. That 0 would feed into here, making the OR a 0 but the not OR a 1. Next, watch the circuit. Remember, when S returns to 0 and R returns to 0, with an input of 0, 0, on R, the NOR gate will maintain the value of Q equal to 1. This is sometimes called an SR latch. Once a 1 is latched into the circuit, it stays a 1. That is memory. When the SR input returns to 0, 0, the Q equal 1 stays. The value of this flip-flop has been set to 1. With a 0 on the R bit and a 0 on the S bit, it should maintain that value of 1. Let's watch it. Follow the arrow. A 0 into here with a 1 means this OR gate would output a 1. Not OR would make that a 0, which would feed a 0 back into this OR gate. Two zeros on an OR gate produces a 0, but not 0 is a 1. So the value of this circuit maintains a 1 as long as the input stays 0 and 0. I'm looking at this line of the truth table. If I maintain a 0, 0 on the SR input, the value of the circuit stays the same. Once I latch a 1 into it, it stays a 1. That is memory. The Q equal 1 remains until it's changed. Let's change this SR latch back to 0. We want Q to equal 0. R is for reset. A 1 on the reset input will change Q equal to 0. SR input of 0, 1 stores a 0 in memory. Look at this line of the SR truth table. With a 0 on the S input and a 1 on the R input, I expect the flip-flop to hold a state of 0. Remember, a NOR gate is not OR, the opposite of an OR gate. Feed a 1 into this gate, and I guarantee you the OR gate will produce a 1. The not OR gate will produce a 0. It will put a 0 on the Q line, which is what we want this circuit to do. That 0 will then feed back into this OR gate with two zeros input to here. The OR would produce a 0, but the not OR would produce a 1. that 1 would feed back into this gate, and that 1 would guarantee or maintain that 0 in computer memory. When R changes to 1, its NOR gate changes to 0. That 0 feeds back into the S NOR gate. With 0, 0 as its input, the output changes. Q naught becomes a 1. A Q naught of 1 will make the circuit maintain a 0 when R returns to 0. Follow the R arrow to see the sequence. Back to where we started. The SR latch is holding the value Q equals 0. As long as the SR input is 0, 0, it will maintain that value. That is computer memory. As long as the inputs to the SR latch are 2 zeros, whatever you last put into Q will be the value that it outputs. If Q has a 0, it will stay 0. If Q has a 1 with a 0, 0 on the input, Q would stay 1. S is for set. When the S input equals 1, the flip-flop will store a 1 and maintain a Q equal to 1. R is for reset. When the R input bit equals 1, the flip-flop will store a 0 and maintain a Q equal to 0. That is 1-bit memory. 8 flip-flops put together could create a byte of computer memory. Flip-flops, 1-bit memory. There is a problem with the SR flip-flop. The circuit barfs when SR input is 1, 1. This is illegal input because both Q and Q naught go to 0, which is 100% bogus. Avoid S input bit equal to 1 and R input bit equal to 1 at all costs. Never, ever let it happen. As long as you do that, an SR flip-flop or a latch will reliably store a 1 or 0 and let you change the value anytime you like. A 16-bit register is 16 of these flip-flops. Again, this is an illegal input. Line 1, 1 of the SR truth table says question mark. I don't know what the output is. If you trace it, a 1 and a 0 into this OR gate produces a 1. Not OR produces a 0. A 0 and a 1 fed into this gate means it produces a 1, and a not 1 produces a 0. I cannot have a 0 on Q and a 0 on Q naught. Basically, 1, 1 on the input barfs this flip-flop. You do not ever want to set both inputs to 1. Set the S input to 1 when you want to store a 1 in this flip-flop. Set the R input to 1 when you want to store a 0 in this flip-flop. And maintain zeros on the input when you want it to hold a bit of computer memory. Let's look at another type of flip-flop called a JK flip-flop. Sequential circuit is a set of gates where the output is determined by the current input and past inputs. In other words, it remembers previous inputs. Behold the JK flip-flop, an alternative to the SR flip-flop. Above is a JK flip-flop, a sequential circuit that remembers if it is storing a 1 or a 0. J is the set input. It can be set to 1. K is the reset. It can reset to 0. Besides using JK instead of SR, the difference? The 1, 1 input is defined for this flip-flop. The 1, 1 input will take a 0 and change it to 1, or a 1 and change it to a 0. The big difference here is this last line of the JK truth table. A 1, 1 on the input says toggle the output. Otherwise, it's very similar to the SR. A 1 on the J bit says store a 1 in the flip-flop. A 1 on the K bit says store a 0 in the flip-flop. And 2 zeros on JK says maintain your memory. Start with JK storing Q equals to 0 and Q naught equal to 1. So I have a 0 on my output Q and of course a 1 on my Q naught. With a JK input of 0, 0, the circuit maintains the output Q equals 0. 2 zeros into J's NOR gate outputs a Q naught of 1. Take a 0 for J and bring it into this AND gate. A 0 into this AND gate will output a 0. A 0 from here would put 2 zeros on this OR gate. 2 zeros on this OR gate is a 0, which means not 0 is a 1, and a 1 will be output as Q naught. If that 1 gets fed back into this OR gate, that produces a 1 for the OR gate, but a 0 for the not OR gate. The J is the set input. JK of 1, 0 says store a Q equal to 1 in the flip-flop. Timing is critical, so I'm using subscripts to show old and new values of the bits. The old value is the main number. The subscript is the new value that it will change to. Let's look at this line of the JK truth table. With a 1 for J and a 0 for K, I should set the value of Q to 1. And there it is. Q is set to 1. Start with a J equal to 1. With a J equal to 1, I will be feeding two ones into J's AND gate. This inputs a 1 into J's NOR gate, which outputs a Q naught of 0. That in turn sends 0 to K's NOR gate, which outputs a 0 for the OR and a 1 for the NOT OR, and Q becomes a 1. That 1 will make its way back to this OR gate and maintain the 1 on Q's output, thereby latching in a Q equal to 1. Everyone see that? The 1 that gets output on Q is fed back into this NOR gate. That new value of 1 in this OR gate ensures that this outputs a 0, and when that 0 is there, it guarantees that 1 stays on the memory. A JK input of 0, 0 says maintain the current output of Q equal to 1. Currently, our flip-flop is storing a 1. If I put a 0 on the inputs of K and J, J is 0, K is 0, this line of the truth table, it says keep the same value of Q. Do not change Q. Maintain the value of 1 in this computer memory. The JK input of 0, 0 makes sure that both AND gates output a 0. This AND gate will output a 0 here. This AND gate will output a 0. With two zeros on the input, both of these AND gates will output a 0. The key to latch is the Q equal 1 that is also input to J's NOR gate. That guarantees a Q naught of 0, which feeds into K's NOR gate to maintain a Q equal 1. Yes, it is circular. That's why it works. The 1 on this output feeds back into this gate, guaranteeing a 1 on this OR gate and a 0 on this NOT gate. A 0 on this NOT will feed back in here and thereby guarantee a 1 there. To write a 0 to the JK flip-flop, set K, the reset bit, to 1. A JK input of 0, 1 will output a Q equal 0. The old and new subscript notation shows the pending changes. The main number is the old value that went into the gate, and the subscript is the new value it changes to. We're looking at this line of the JK truth table where J equals 0 and K equals 1. K is the reset bit, so we want to reset this memory to 0. Follow the arrow K equals 1. If I input a 1 for K here, the JK input of 0, 1 makes K's AND gate output a 1. There's a 1 here and an initial 1 on this AND gate, so two 1s on this AND gate produces a 1, which sends a 1 to this OR gate. That inputs a 1 to K's NOR gate, latching in Q equals 0. With a 1 into this OR gate, it becomes a 1. Not OR makes it a 0. I'm outputting a Q of 0. That 0 feeds into J's NOR gate and changes Q naught to 1. Two zeros on this OR gate, not OR becomes a 1. That 1 then feeds back into here and will guarantee that this maintains a 0. There's a timing that goes on here. The initial 1 that latches in the 0 gets sent back, fed through this loop, and comes back here as a 1, which means it locks in the 0. Takes a little while to get used to it, but once you start understanding the timing of the circuit, it works. A JK flip-flop can store a 0 or 1. We're back to where we started. With a Q equal to 0 and a JK input of 0, 0, the JK flip-flop will maintain that Q equal to 0. That is computer memory. The key is the Q naught equal to 1 that feeds into K's NOR gate. It makes sure the circuit maintains a Q equal to 0 output. See this 1 right here? As long as there is a 1 on this OR gate, not OR will be a 0, and this flip-flop will maintain a 0 state. The two zeros on the input means the other two inputs here have got to be 0. This line is what determines what the gate outputs. With the previous output of Q equal to 0, a JK input of 1, 1 will toggle to Q equal 1, or change a 1 to a 0 if it started at 1. Just focus on the output of the JK AND gates. We're doing this line of the truth table with two ones on my JK input. Toggle the bit. If it was 0, toggle it to 1. If it was 1, toggle to 0. Two ones on J's AND gate is J equal to 1, so the 1 will pass through to this OR gate. With a 1 on that OR gate, it guarantees that the NOT OR will output a new value of 0. When the NOT OR inputs a new value of 0, that OR will fit into this gate. With two zeros on the input of this OR gate, NOT OR becomes a 1, and the 0 toggles to a 1. What happens when Q equals 1? Look at the subscript. K's AND would then be 1, 1. J's AND would be 1, 0. The K reset bit toggles Q from 1 to 0. Most JK flip-flops have a clock or enable line into the AND gates. When that line is 0, JK is 0, 0 at all times. Q stays the same. When that line goes to 1, Q now can be changed. The AND gates decide if the JK signals get through. Remember the decoder circuit at the beginning? It can decide which register should be write enabled and latch the ones and zeros from the data lines into their memory. This is a clock or enable line. If it is 0, then these AND gates always have 0 and we're permanently stuck with JK of 0. When this line goes to 1, then one of these AND gates can go to 1. And only then. This is a clock or enable line that says activate this flip-flop. Flip-flops, 1-bit memory. Let's look at a D flip-flop now. A sequential circuit is a set of gates where the output is determined by the current input and past inputs. In other words, it remembers previous inputs. This is the D flip-flop. Above is the D flip-flop, a sequential circuit that remembers if it is storing a 1 or a 0. Just one data input D to this circuit and a required clock or enable line E. When the circuit is enabled, D equal 1 means Q should be set to 1. When D equals 0, it means Q should be set to 0. What if it's not enabled? Q stays the same. When D is 0, Q should go to 0. When D is 1, Q should go to 1. And that only happens when E goes to 1. As long as E is 0, nothing changes on this flip-flop. It maintains its current output. Here is a D flip-flop with the enable/clock bit E equal to 0. Cold hard fact number 1. An AND gate with a 0 input will output 0, and that's what's being shown here. All I want you to concentrate on is this 0 for the E input. A 0 fed into this AND gate guarantees a 0 out. A 0 fed into this AND gate guarantees a 0 out. With two zeros on the inputs of these NOR gates, I maintain the value of Q. Cold hard fact number 2, a NOR gate with 1 0 input will output the opposite of the other input. A 0 0 NOR gate outputs a 1. A 0 1 NOR gate outputs a 0. This guarantees when E equals 0 will keep Q the same. Q equal to 1 stays 1. Q equal to 0 stays 0. With E set to 0, Q stays the same. Follow the arrows when D equals 1 and E equals 1. See the 1 going into the lower NOR gate? Cold hard fact number 3. A NOR gate with at least one input will output a 0. Follow this 1. It's fed into this AND gate. With two ones on this AND gate, we'll put a 1 on this NOR gate. A 1 on this NOR gate guarantees a 0 on the output. As soon as a 1 comes out of the lower AND gate, it means a Q naught equal to 0 must come out of the lower NOR gate. That 0 goes into the upper NOR gate, forcing a Q equal to 1. And there's the 1 being stored in the flip-flop. That 1 is fed back into the lower NOR gate to make sure that that Q equal to 1 after E gets reset to 0. How does that guarantee it? At least 1 on this gate here guarantees 0 here. A 0 into there guarantees a 1 coming out there. Follow the arrows when D equals 0 and E equals 1. See the 1 going into the upper NOR gate? Cold hard fact number 3. A NOR gate with at least one input will output a 0. With a 1 being fed into this OR gate, it will guarantee that the NOR gate will output a 0. As soon as the 1 comes out of the upper AND gate, it means Q equals 0 must come out of the upper NOR gate. We're doing this line of the truth table. D is set to 0 when E gets enabled to 1. A 0 fed into this NOT gate puts a 1 here. A 1 on the E gate puts a 1 out of this gate. That 1 guarantees a 0 here. That 0 then goes into the lower NOR gate, forcing Q naught to 1. That 1 is fed back into the upper NOR gate to make sure that Q gets reinforced to 0 after E goes back to 0. Whew, that's it for flip-flops. Make sure you know the truth tables for the SR, JK, and D flip-flops. Also know the truth tables for the gates NOR and etc. These flip-flops were built out of NOR gates. They can also be built from NAND gates. The internal logic of the circuit is different with NAND gates, but the Q and Q naught outputs are identical. Know your sequential and combinational circuit differences. Sequential circuits can maintain a value in memory. A combinational circuit only has an output based on its current inputs.
Kingside.com.